Hey Calc students, I got a few questions about number 33 from the homework, a little bit in office hours last week, also an email over the weekend. So I thought it'd be worth reviewing this one. It also gives us a chance to look at a few things. Chain rule, an interesting situation with closed intervals and the closed interval method. All right, and it's got some interesting algebra in it as well. Okay, so find the dimensions of the isosceles triangle of largest area that can be inscribed in a circle of radius r. All right, first thing, we need a circle. And I'm going to draw an isosceles triangle. I'll orient it vertically here. And this length would be the same as that length. Now, we know it's a circle of radius r, so if this is the center, the radius goes up to here. I'll label that r. The radius also goes to these corners, r, and the radius goes to this corner, r. And this is helpful because we can put some variables on this, and there's a little right triangle that's going to be helpful. Now, to get the area of the isosceles triangle, we need to use the height of that triangle, and we need the base of the triangle. So we need some more labels here. Let's label this little length A, and then this length X is going to be that dashed height, and that's going to be our variable height. So if X gets longer than what you see, if X were this long, then this base would be more narrow, and the triangle would be taller. If X is 0, for example, that means the base of the isosceles triangle is this diameter. And if X were negative, like here, that means X would be like a negative value. If X were negative, the base of the isosceles triangle would be here. And we get all these different isosceles triangles. If X is negative r, it's reaching this side, and if X is r, it's reaching that side. Okay, so we can write a function. So let's write a function, area. Clearly the area is 1/2 base times height, base of the triangle, height of the triangle. But the base is 2a, and the height is r plus x. Now I'll change that to green because I labeled a in green. Now we need to sub out a. Now remind yourself, r is a constant. In this problem, it said the circle has radius r. If that's fixed, it's not changing. Only x is a variable here. Now a is a variable because as x changes, a changes. But let's eliminate a. So first thing is we need a, which is equal to the square root of r squared minus x squared. Okay, so it's a little Pythagorean theorem from the picture. These 2's cancel, and the a is square root of r squared minus x squared, and times r plus x. Okay, I'm going to put an a of x here, and we've reached the first important thing on any optimization problem. After you draw the picture and label your things and you get your relationships, you need to get to a function of a single variable, x in this case, r is a constant, and a single output, a, and a is the thing you want to maximize. The output is the thing you want to maximize or minimize in the optimization problem. Okay, let's think about the domain of this function. That's going to be important. We already mentioned it earlier, but the least x could be is negative r. That would be where this length is actually up here on the top. And it can't, if x is negative r, you get an isosceles triangle of area 0. It's like theoretically the endpoint, but it's not that interesting. But we can include negative r in the domain. Now the max x could be is r. Great. Well, if x went past r, there wouldn't be a triangle inscribed in the circle anymore. And if x went past negative r, you'd have like negative height, which makes no sense. So this is the domain of this function. Those are the endpoints. Okay, now a prime of x is just a little bit of product rule and chain rule. Let's just write the first factor as is and multiply by the derivative of the second factor, but that's just 1 because the derivative of r is 0 and the derivative of x is 1. Okay, so then we add, product rule, the second factor times the derivative of the first factor, 1/2 r squared minus x squared to the negative 1/2 times negative 2x. Okay, so just a quick note to say, well, actually, let's clean this up first. Square root of r squared, let's see, square root of r squared minus x squared. The 2's cancel. That becomes a minus. In the numerator, I'm going to have x times r plus x. So the numerator will be rx plus x squared. And in the denominator, I will have square root of r squared minus x squared. Okay, so for a couple things first, we'll solve for this equal to 0 in a moment. Let's notice that this is undefined when r squared equals x squared, because it would make this denominator 0. And that's true when r equals plus or minus x. Or when x equals plus or minus r, I guess, because we're solving for x. But in any case, we see that the endpoints of the domain actually make the derivative undefined, and they're in the denominator. The denominator is going to 0, so this looks like it's going to have vertical tangents at the endpoints, or at least it's going to be approaching vertical at the endpoints. Okay, now let's solve for where it equals 0. Okay, so if I set the derivative equal to 0, I'll do one step of algebra. So we'll set this equal to 0 and take this term and move it over to the other side. Okay, so that would give me rx plus x squared over the square root of r squared minus x squared equals the square root of r squared minus x squared. You know, we're assuming this can't be 0 in the denominator. I can multiply through by the root. I get rx plus x squared equals r squared minus x squared. Okay. Great. So we just collect terms. We get 2x squared plus rx minus r squared equals 0. And this is nice because this actually factors. So we get what? 2x. And then there's going to be an x here, and this has to be an r and an r. And with a little checking, you can see that there has to be a plus and a minus here. And just double check that there's no mistake. 2x times x is 2x squared. Negative r times r is negative r squared. And then 2x plus r is 2xr. So 2x times r is 2xr minus xr is 1xr or 1rx. Okay, so the solutions here are when x equals r over 2 or when x equals negative r. Now, is this really a solution? Remember, we were solving for when a prime of x equals 0, which was, we're solving this equation right now, and that's this equation. But remember, whenever you multiply through by variables, you can always introduce extraneous solutions. We've actually already found that this must be an extraneous solution because it actually made the derivative undefined to begin with, and you can see that actually right here. So if you plug this into here, this term is, this expression on the left is undefined. So this is actually an extraneous solution. So this is the only critical value that is in the interval. Now r over 2 is clearly in the interval. Because it's, r over 2 is between negative r and r. And now we just need to do the closed interval method. So for the closed interval method, we will have x values and a of x values. And we want negative r, that's on one endpoint. And we want r over 2, that's on the other endpoint. And r is on this endpoint. Well, just very quick inspection. If you plug negative r in for x, this whole thing is 0. And that actually makes sense because just geometrically the area will be 0. You get the same thing if you plug in r to the function. Now, why is that? Because if you put r here, you'll get r squared minus r squared there. So in either case, you get 0. So we need to plug in r over 2 into a of x. So a of r over 2 is the square root of r squared minus r over 2 squared times r plus r over 2. And a little bit of reduction. Let's see what we get. R squared minus r squared over 4. And we get what? 3r over 2 equals. Yeah, let's see. So we get the square root of 3r squared over 4 times 3r over 2. And we have what? We have r times 3 times r times root 3 over 2 times 2. And we get what? 3r squared root 3 over 4. Now let's think about what this really means and what really matters. So this is 3r squared root 3 over 4. And what we found is when x is r over 2, this is the area of the triangle. Now, if you go back to the question, the original question didn't actually ask for the area of the triangle. So this whole calculation was just done to verify that this is positive. Since this is positive, it's greater than 0, and therefore we know intuitively this has to be the absolute max. Okay, so what all that matters here is this is greater than 0, and since this is the greatest value via the closed interval method, then this is the absolute max, and r over 2 is the length for x that maximizes the area of the triangle. Okay, so x equals r over 2 maximizes the area. And I could also say let's just say here that by the closed interval method, and of course, just for our sake of studying and remembering the theorems, this is justified by the extreme value theorem. We have shown that x equals r over 2 maximizes the area. Okay, and let's just double check we've answered the question. Find the dimensions of the isosceles triangle of largest area. Okay, so if x is r over 2, and therefore the height is r plus r over 2. That was from our picture. So remember the height was r plus x, so it's r plus r over 2. And to get a, we would just need to plug our x value in here. So that would be, so that's our height, and then the base would be 2a, which is the square root of r squared minus r over 2 squared. Sorry, 2a, which is 2 times that. Okay, the base is 2a, which is 2 times that. So this is 2 square root of r squared minus r squared over 4, which is 2 square root of 3r squared over 4, or 2r root 3 over 2, or r root 3. Let's just check that. Yep, that's it. Okay, so our the height of the triangle is r plus r over 2, and the base of the triangle is r root 3. Key facts here: we needed to set up the function and use find the domain of the function, which had a closed interval, and use the closed interval method to justify that r over 2 was the max.